Okay, so solving inequalities. Solving inequalities pretty much like solving equations. There'll be some differences, which at this point you should remember. Right? So remember, inequalities are one of these four. We know that like graphing an inequality means you're going to graph either open or closed circle on the number. If it's or equal to, it's closed circle. If it's not or equal to, it's open. Right? There's shading to the right or to the left. If you're not sure where the shading goes, if you solve for the x on the left, then the inequality symbol is like pointing the way to the shading. Right? That's if the x is on the left. Right? How many solutions are there to an inequality? Infinitely. Infinitely many, right? Unlike an equation where we usually get like one solution. In this case, this continuous red line means that every little point on that line, there's another solution. And if you want to zoom in and it exposes some more points, then those are included too. And you can keep zooming in and there's more and more and more. Infinitely many solutions. Because you guys are coming, most of you coming from an Algebra 2. I can't really do it there anyway. We'll do it here. I'm not sure if any of you got this, but you might have had like somebody show you how to do this with interval notation. Like if I wanted to say that this starts at 4 and goes infinitely to the right, then I say it like this. I put a parenthesis for 4, and it's parenthesis because it does not include 4. And then on the right side, it goes until infinity, positive infinity. And then for infinity, you never put, you always put the round bracket for infinity because it's never included in the answer. So what do you put if it's a or equal to in a closed circle? Then you use a square bracket to say it includes that point, 4 to infinity. Right? How do you think we would say this one, which is x less than 4, what would be on the left side of that interval? Negative infinity. And where does it stop? Stops at 4. Does it include 4? No. So we're going to go like that. And then this one would have been negative infinity to 4, but it's a square bracket because it includes the 4. How many of you have seen that interval notation before? Anybody? In pre-calculus, they deal with that quite a bit. In algebra, I was tutoring a kid from Bethel the other day, and they were doing that on what they called set builder notation. Like, in order to write the first one, this is what they would do for what they call set builder notation. They would say, this is the answer. The answer is the set of, and that's where that curly bracket comes from. Those are set brackets. The set of all x, and then you write a bar. That means such that. And then you would say, x is greater than 4. I mean, I think sometimes on the SOL they did use that kind of notation, but the big thing to keep in mind is just the x greater than 4. I don't even know why they keep doing that. Sets, doing sets and properties and all that stuff is something that they started in the 1960s. And, what happened is, how many of you know about Sputnik? You probably studied that in some other class sometime, right? So in the late 50s, the Russians sent up a satellite, and we were like scared to death. We're not only scared because this thing could fly right over us. What if they drop a bomb on us, But we're like, we're behind. We don't have a satellite up there. They're ahead of us. What are we going to do? So they turned to education, and they said, well, we got to do something better with our math and our science. That's it. And for the math, they turned to really a bunch of university people who came up with what was called at the time new math. And new math introduced all those properties and set things. And really by the end of the 60s, parents were so upset because they didn't understand it. They weren't taught that way. And basically the new math mostly went out the window. But there's some of this stuff we still deal with. I think before then, we probably always knew that if you add two numbers, it doesn't matter the order. But starting in the 1960s, we had to know the property name. We had to like justify every step. Pretty sure before that we didn't. But that's why I don't like teaching that part of it. The kid I was tutoring was getting all the math right and then getting hung up on this notation stuff, which to me is kind of not productive. Okay. So how do we isolate the variable in an inequality? Pretty much like you isolate the variable in an equation. You do operations to both sides until you've got only the variable on one side. There's only one big difference here, and that is when you multiply and divide by negative, what do you have to remember to do? Flip the inequality symbol, right? Other than that, everything works pretty much the same. We've got an addition property of inequality, just like we got an addition property of equality. So keep in mind, those are the main things, right? Multiply and divide by negative, remember to flip the symbol. Okay. Okay. Don't eat in here. Okay. Don't eat it. Do not eat it, right? Okay. So why is that? Why is that thing we got to flip the symbol? Well, I mean, if you take like 2 and 3 on the number line, right? 2 is less than 3. It's to the left of 3. But if I multiply by negative 1, right, I get negative 3 and negative 2, and now negative 3 is to the left of negative 2. That's why you've got to do that. Right? Because the way the numbers get bigger as you go away from 0, right? In the negative numbers, that makes negative 3 less than negative 2. That makes 2 less than 3. Okay, so let's do a solve. So again, before we start doing those equations of inequality, properties of inequality, we've got to simplify on the same side. Right? So what do I have to do to simplify the left-hand side? Distribute, right? So I've got to get negative 6x plus 15 plus 1 is greater than or equal to 4. Next, combine like terms. Negative 6x plus 16 is greater than or equal to 4. What are the last two steps? Subtract 16, divide by negative 6, right? Minus 16. What did I do that for? Let's fix that. So minus 16, minus 16. Now I've got negative 6x is greater than or equal to negative 12. Divide by negative 6. Divide by negative... Oh, sorry. I meant to not do that. What's wrong? If I just say divide by negative 6 right away, you got to flip the symbol. And so I don't want to go and just like right away. If I write the negative 6 at that moment, it's wrong. Unless I go back and erase right away. And I don't want to do that. It's kind of hard to take notes when somebody's like erasing what was there before. I used to have a professor at University of Utah, and I mean, he would be writing these immense, proofs of complex calculus equations that talked about radiative transfer of the atmosphere, and he would just he'd be writing like that, and then he'd go, and then write it in, and like you're copying all these notes, and then what did he just do? What did he just do? I don't like that. So instead, what I'd like to do is just write it on a new line. Just at this step, I'll say negative 6x divided by negative 6. Now I'll flip the symbol. Negative 12 over negative 6. Okay, so now x is less than or equal to 2. So there isn't a line where it looks wrong. Okay, now how do I graph that? For me, it's okay if you just put the 2. Open or closed circle? Closed, left or right? left.
Pointing to the way it's supposed to go.
Right. Well, I mean, X, you mean, think of the X as like representing the shading. It says the shading is less than 2. Well, on a number line, less than means on the left side. Okay, so the shading should be to the left of 2. Okay, this is easy stuff, right? Too easy. So try that one. So first I've got to distribute. Negative 2x minus 18 plus 5 is greater than or equal to 3. Combine like terms. Negative 2x minus 13 is greater than or equal to 3. Right? Add 13. Negative 2x is greater than or equal to 16. Okay, now I'm going to divide by negative 2, so I'd write a new line, and at that point I switch the symbol. Right, so this is x is less than or equal to negative 8. So as a graph, negative 8 looks like it's closed circle, shaded to the left. Right. Not a mystery. Okay, so on the top of the screen from here all the way down to here, right, that's a worked out word problem. Okay, so this on the bottom is a similar word problem that you should be able to use this to model your solution after, right? So let's read through this and then you guys are going to work on that. A movie rental company offers 2 subscription plans. You can pay $36 a month and rent as many movies as you like, or you could pay $15 a month and then pay $1.50 for each movie that you rent. How many movies must you rent in a month for the first plan to cost less than the second plan? So what they have worked out here is kind of like the problem-solving template they always give us. You know, first you get a problem, a real-world kind of problem. You try to understand the problem. At that point, you could see what they did. They defined their variable. Let's let n be the number of movie rentals, right? Then they found expressions to represent the 2 plans. The first plan always cost 36. The second plan cost 15 for a month, and then $1.50 for each additional. And we want to know when is it that the first plan is less than the second plan. So at that point, they've modeled this real-world problem with a math problem. Okay, so that's the end of step 2. Step 3 in the problem-solving thing is, okay, solve the math problem. Right? What are the 2 steps that you would have taken here? Subtract 15, divide by 1.5, and then you get an answer. And then the last step is, okay, what does that answer mean in the context of the problem? N is less, 14 is less than n. It looks like then you would have had to rent more than 14. So like 15, right? And then the first plan would have been cheaper. So this here, now this is talking about a digital music service offers 2 subscription plans. The first has $9 membership fee and charges $1 per download. The second has a $25 membership fee and charges 50 cents. How many songs must you download for the second plan to cost less than the first? So try to do that one. You've got this to look at, the pattern your work on, see what you come up with. Okay, so did you define your variable? I mean, it helps sometimes to define the variable, really. But, you know, if you just march right into it, it's probably okay. So n maybe is the number of downloads, right? Yep. Downloads. Okay, what was the expression that represented the cost of the first plan? 9 plus n. Okay. What was the expression for the second plan? 0.5 times n. Okay, we want to know how many songs makes the second plan cost less than the first. So which inequality symbol is going to go in the middle of those 2? It should be greater than, right? So the first plan costs more than the second. Okay, and then at that point it's a matter of solving, subtract 0.5 times n minus 0.5 times n. So 9 is, oops, that was wrong. 9 plus 0.5 n is greater than 25. Subtract 16. 0.5 n is greater than, subtract 9 and get 16. And then divide by 0.5. N is less than, n is greater than 32. Now, would it make sense in that case to graph this? Like here's 32, and it's open circle, shaded to the right. And the answer is no, that wouldn't make sense, because can you rent like fractions of a movie? No, I mean you really only have 33 and 34 and 35, right? The integer values. That's all you would have. So really this wouldn't be a case to graph. Okay. Yeah.
So on the top right there, why is it subtracted 0.5 and subtracted the other side? Isn't n minus 1 not negative?
It's 1. It's here. It's 1n minus 0.5n, which is plus 0.5n. 1 minus 0.5 is 0.5. 1 minus a half is a half.
So after you did the 0.5 n is greater than 16.
Hey, quiet please. What's that?
So after you did the 0.5 n is greater than 16.
Yeah. What did you do? You divide by 0.5. Like that. Okay, so that is a word problem. Yoo-hoo. Okay, next. I'm going to solve this one. First step, distribute. Okay, now I've got negative 6x on both sides. If I add 6x, then all the x's cancel, and I get negative 2 is greater than 7. Right, so this is like with equations, right? If you cancel all your variables and you're left with a statement which is true or false, right? The answer doesn't depend on the variable anymore. It's either always true or always false. In this case, is that true or false? False, so it's always false. So what do you say if it's always false? No solution, right? False. No solution. Right? What about, wait, somebody? Okay, let's look at this one. Distribute. Okay, stop talking, or else I'll make your classwork as 0 for the day, okay? Okay, combine like terms. 3x minus 15 is less than or equal to 3x plus 8. Again, got a 3x on both sides, cancel. So minus negative 15 is less than or equal to 8. So no variables involved. It's either always true or always false. Is that true or is that false? That's a true statement. Negative 15 is less than or equal to 8. That's true. Okay. So when we did this with equations, what did we call that? An identity. But this is not an identity. You wouldn't call it that. But what would you say is the solution? All real numbers. So any value you plug in is going to work for this. All real numbers. Okay, what do you think the graph of all real numbers looks like? the whole number line, right? It's all included. Yeah. Negative infinity to positive infinity. It's all there. Okay. All right, try that one. Okay, just distribute on both sides. 8x minus 12 is less than 8x plus 8. Subtract 8x. Negative 12 is less than 8. All right, so that's true. So we're going to say all real numbers. Okay, so you'd say all real numbers. If you use that interval notation, that's negative infinity to positive infinity. If you use that set builder notation, and I've seen this on the Algebra 2 as well, which you don't care about anymore, but you may remember seeing it. Sometimes they give us like in the training materials, like the release stuff from the past. You would say it like this. The set of x such that x is, and this is math stuff, it's like an E like that. That means a member of, and then you use a fancy R. That means x is a member of the real numbers. Okay. Math trivia. Okay, let's see what I got left. So compound inequalities is when you've got more than one inequality and they're joined by the word and or. Right? So for an and to be true, both have to be true. For an or to be true, just one has to be true. It's okay if both are true, but at least one has to be true for an or. And this is not just a math thing. Like this is just the way the words work, and an or. Like if I make a statement, we're going to dinner and a movie, but we only go to dinner, is my statement correct? It's not correct, because an and implies you're doing both things. But if I say we're going to Target or we're going to Walmart and we go to Target, was my statement true? Sure. That was no implication of doing both. So that's the way and or work. Many years ago, like probably 2004, when I was in the Air Force, I was on a court-martial board for somebody. And, her unit was deploying to Iraq. And when they were all deploying, she was in her car driving across the United States trying to go the other way. And so, that's not okay with the military. So there was a court-martial. And by the UCMJ, Uniform Code of Military Justice, the thing that she was charged with, it would had an or in there. It was like either this or that. And there was a point in our deliberations when, some of the people there were definitely saying, well, since she didn't do both, she's not guilty. And I had to bring up that's not what the or means. It doesn't, she only had to be, guilty of the one. And that was the obvious point. So she was found guilty. That was the only court-martial. I never had to do a jury either. I got called to jury duty, but I wasn't picked. Darn it. Anyways. Okay, so here's an example of a compound and. Remember, for an and to be true, that both have to be true. And notice it says graph the solution. For these compound inequalities, that's kind of how you get the understanding out of it, is by looking at the graph. So let's say on this one, if I subtract 1 from both sides, I'll get 6 is less than 2x. Then I divide both sides by 2. 3 is less than x. Okay, on this one, I just got to divide by 3. X is less than or equal to 6. Okay, now, as an answer, that's okay. You're almost done. You just write this, and you put an and in the middle. It's 3 is less than x, and x is less than or equal to 6. Right? That's enough of an answer. Now, if I look at the graph, all right, 3 would be on the left, 6 would be on the right. Okay, let me change colors here. Okay, let's do the x less than or equal to 6 first. Open or closed circle? Closed. Left or right? Left. X less than or equal to 6. Okay, what about the 3 less than x? It's open circle, but which way do you shade? To the right. Okay, remember that if you solve for x on the left, then you can use the inequality symbol to point the way. The x is on the right. And if it helps, because this is the place we make a lot of mistakes, you could just switch the sides, right? If I put the x here and I put the 3 there, then obviously I got to switch that symbol to be like that. Okay, now you can use the arrowhead, approach. So this one will go like that. Now, for an and to be true, they both have to be true, right? Are they both true less than 3? No, only this one is true less than 3. Are they both true greater than 6? No, only this one is true greater than 6. Where are they both true? In the middle of 3 and 6, right? That's what a compound and looks like. It's the middle part of the number line. So if you do it like this and you show the 2 different shadings, you got to go back and say, okay, that means this is the area that's the solution. And then if you're looking at that, it actually brings up, there's a little better way to write the answer than like this here. Instead, write it like with a 3-part inequality. 3 is less than x. It's less than or equal to 6. That's really the way you would see the answer. You wouldn't see it as 2 different inequalities. But you're not wrong if you do it the first way. Right? I mean, I would still count it, but I would recommend you do the 3-part inequality. Okay, that's an and. Which one? What? This? That's correct. I just said I would take that if you did it. But it's better to do this. Okay? You have a question? Okay. So let's try. Here's an or, right? 2 pretty simple inequalities. Subtract 7. And we're going to get k is greater than or equal to -1. And then subtract 8. K is less than or equal to -5. Okay, so those are the 2 solutions to the individual inequalities. Okay, they are the right answer, provided you have the word or in between. It is not all the way right unless you put the word there. Okay, now let's look at that on the graph. So -5 goes to the left, -1 goes to the right. So greater than or equal to -1 should be closed circle, shade to the right. Less than or equal to -5, closed circle, shade to the left. Okay. Now, are we looking for the overlap this time? No, it's not the and. That's what the and. In this case, this one is true to the left of -5. This one is true to the right of -1. Together, that's the graph. So you just put them all together. That's it. Oh, that's a mistake. That's a mistake. Sorry about that. So let me try to make a really fine little erase here. And then let's see if I can get the middle out of that. Oh, that's the -5. I need to do it over here. That's pretty good. Okay. So with a compound or, that's kind of what it looks like. Okay. You could think of it that way if you want. It's not always going to be true. Take, for example, and this is a different problem altogether, right? But take, for example, if you had something like this. Let's say we have x is greater than 1 or x is greater than 2. Okay, look at that in a number line. 1 and 2. So let's see. The first one would give me open circle, shade to the right. The second one give me open circle, shade to the right. So now what is the graph of the compound inequality? It's actually everything to the right of 1. And there is no break in the middle. Now when we get to the next lesson and we're doing absolute value inequalities and absolute value greater than specifically, then it will always be that case that it's the two sides that are covered in the middle that it's not. But you could come up with compound inequalities that are not from absolute value that have all kinds of different shapes like that. What would be the solution of this one if this OR was an AND? Then what would be the graph of the solution? We said the OR started here and went to the right. Where would the AND start? It would have to start here, right? Because you need the overlap. So it would start there. Just there. Okay. So try this one. There's an AND. Okay, quiet please. So let's solve them both. Add 1. That 6 is less than or equal to 3x. Divide 3. 2 is less than or equal to x. And if it helps you, you could like switch the sides of that. That's like saying x is greater than or equal to 2. All right, this one, divide 2. So x is less than 6. Right, so if I graph those on a number line, 2 goes here, 6 goes here. Closed circle on 2, shade to the right. Open circle on 6, shade to the left. Okay, it's an AND, so I need to say I only want where it overlaps. That's between 2 and 6. Right? For the answer, not just the graph, I can write it like this. I can say x is less than or equal to 2 as long as I use the word and x is less than 6. Or I could use a 3-part inequality. Less than or equal to x, less than 6. Okay. Here we go. Try that one. Here's an OR. Act 1. 15 is less than 5x. Divide 5. 3 is less than x. Subtract 9. 3x is less than negative 3. Divide 3. X is less than negative 1. All right, so the answer is these two with an OR. And the graph has negative 1 on the left, positive 3 on the right, open circle on both. Okay, if 3 is less than x, then x is greater than 3. Sorry. Yeah, so that goes this way. And x is less than negative 1 goes this way. And since it's an OR, you're not looking for the overlap. You just add those two areas together. That's the graph. Okay. All right. So let me graph these two just to show what goes on. Where? Okay, quiet please. So here, remember, you don't flip the sign because this is a negative. You would flip the sign because what you were dividing by was a negative. Okay? There's more than one that made that mistake when I was going around. It's what you multiply or divide by that determines whether you flip the sign. Okay, Bryce? Okay, here we go. So let me, just to show what this is real quick. If I have 2 and 5, right, greater than 2, open circle, shade to the right, less than or equal to 5, closed circle, shade to the left. Now this is an OR. So what is the graph of the compound inequality since it's an OR? Remember, for an OR, what has to be true? Just one, right? So look to the left of 2, one of them is shaded, right? To the right of 5, one of them is shaded, and in between 2 and 5, they're both shaded. So what parts of the number line are included? The whole number line, right? So the solution is all real numbers. So I'll go like this. Use my highlighter. It's the whole thing. Okay. What if it was like this? Two to the left, 5 to the right. Right? It's less than 2 and greater than or equal to 5. Okay, but it's an and. What do you look for when you're graphing an and compound inequality? You're looking for where they overlap. Okay, so where do they overlap? They don't, so there's no solution. Right, so that's why you always want to graph it, because the graph of it might inform your final answer. So this is no overlap, so no solution. Okay, one more little thing, and then we're done. So 3-part inequalities, again, we've seen them a little bit as a way to express an answer for a compound and. But sometimes you're presented with these things to solve, like there's an expression in between the two inequality symbols, right? So you should think of it as the values for this expression here are between 1 and 9. Right? They have to be more than 1, but they have to be less than 9. So you solve something like this, right? You isolate the variable in the middle section by doing operations to all 3 parts. You could consider it's like a compound and, right? It is. You could think of it like 1 is less than 2x plus 3, and 2x plus 3 is less than 9. And you could get it right if you do it that way, as long as you use the word and, then I would count it. But in math, you'll never see that in the textbook. For a problem like this, they would expect that you did it like a 3-part inequality. And we don't want, if we are, you guys have seen these before. If we are a little uncomfortable with 3-part inequalities, maybe we get a little more comfortable with a little more work with them, because they happen. Okay, so here's the example. Minus 3. If I minus 3 there, I've got to do it 3 times. So negative 2 is less than 2x is less than 6. Divide by 2 once, twice, 3 times. So I get negative 1 is less than x is less than 3. Now, how would that have been different if there was a minus in front of the 2x right there? Yeah, when I got down to, if that was a minus and that was a minus, then at this step I'm dividing by minuses, and now I got to flip both of those symbols to make them greater thans and greater thans. So that can happen, like in the last step, you end up flipping all the less thans to greater thans. But what you need to be careful about is that somehow you're out of all that confusion, right, is that it needs to be a transitive property here, right? If negative 1 is less than x and x is less than 3, then this number must be less than that number. And if you end up flipping the symbols, again, make sure that that number ends up being greater than that number, because sometimes we do make mistakes on that. Okay, so that's how you solve a 3-part inequality. Try to do that on this one, and then we're done. That's your you try. Subtract 2 once, twice, 3 times. 9 is less than 3y is less than 18. Divide 3. Once, twice, 3 times. 3 is less than y is less than 6. And it didn't say to graph, but if I graphed, remember, a 3-part inequality looks like this, right? It's open, open, shaded in the middle. Okay, that's it. So we solved and we graphed. And we did a real world, a practical problem, that one. That's the homework coming out of your workbook. You got time, so you need to be working on it. It's part of the class.